Alright, so in this video, we're going to look at page 30, where we talk about simulations. So it gets right to the point. Simulate 7 rolls of a fair die and find the probability of getting a 4. Right? So let me just fix the notation here. Alright, so what you're going to do is you're going to go to Desmos, but if you do it through Blackboard, you click on Calculators, Unit 2, you'll see random numbers. All right, so it'll be the random number calculator in Desmos. Very straightforward. When you're designing a simulation, it's really not the challenge to come up with the numbers, it's the challenge to decide what those numbers represent. So what we're going to do is come up with a rule that allows us to randomize using the technology. All right, so we know that a die, I included an unfolded die here, we know that a die has 6 sides. 1, 2, 3, 4, 5, and 6, represented by the dots. But the number 4 is the one that we're looking for. All right, so if we were to develop a set of random numbers, only going from the numbers 1 to 6, only integer values, then I would only be concerned with how many times the number 4 occurred in the number of trials that we had. All right, so we have a bunch of different options here. We have this capital N that represents the number of random numbers desired. We want 7 rolls of a fair die, so let's make that a 7. Now, we have different options here. I wrote this script myself, so it's limited in a sense, but that's a good thing because it's focusing specifically on the types of randomization that we would be interested in this class. So random numbers between 0 and 1, so decimal values, random numbers between some number A and B and some number B, random number based on a normal distribution, and random number based on a binomial distribution. We're not there yet for those ideas, but we are here with the idea that we want to have a random number between some value A and some value B. I defaulted it to 1 and 6 because it's very typical that you work with dice when it comes to probability, dice, cards, things, coins, things like that. Okay, so if it was not set to 1 and 6 for A and B respectively, you would just toggle these slide bars, I guess, so that the lower one is 1 and the upper one is 6. All right, so you always want the lower one obviously to be smaller than the upper one. All right. So if you only wanted a single random number, then you would just go to where it says single random number. But if you want all n of your random numbers in one shot, you see it says 7 element list, you go right to the table, and what it did was it simulated 7 rolls of a fair die. All right, so our 7 rolls would give a result of 2, 5, 5, 2, 6, 4, and then you got to tap on it or click on it and then scroll down a little bit to see the 7th value, which is another 4. All right, so 1, 2, 3, 4, 5, 6, 7 outcomes. So our experimental probability is, well, we got 2 4s out of 7 outcomes, so 2 out of 7. All right, so we know that the probability of getting a 4 should be 1 out of 6. 2 out of 7 is not equal to 1 out of 6, but you get the idea that hopefully if you try this many times for a larger and larger sample size, so instead of going up to 7 trials, maybe you go to 10. Oh, I missed. Go to 10. Or if that's insufficient, maybe make that, tap on it, make that 10 into 100, And then you can get into your table and you'll see that there's a whole lot of outcomes here. All right. So if you go down that list, you could see how many 4s you would have out of the 100 trials. So maybe 2 out of 7 isn't close. It's actually not too far away, but maybe it's not close enough to 1 out of 6. But I'm willing to bet that if you increase the number of trials sufficiently, that you'll get something that's very, very close to the number that you're looking for or interested in. The idea behind this technique is generally we use it when we have no idea what the probability is. And here we're just kind of using a familiar instance so that we can verify that the technique works. Now, for those of you who are following along saying, I got something different, that's fine. We're simulating. These are random values, all right? These are random values. My random would be different from your random. I mean, you got to imagine that if you had your own die and I have my own die and I roll my die 7 times and you roll your die 7 times, we're not going to always get the same outcomes. So it would make sense that using our simulation, in fact, I would be surprised and I don't want to say disturbed, but I'd raise an eyebrow if we all got the same outcomes. All right. So let's move on to number 2, again, the notation. I got to fix that in the master document. Simulate 300 rolls of a fair die. Well, I showed you how to do 100 rolls and find the probability of getting a 4. So let's do 300 rolls. All right, so I got 300 rolls, still from 1 to 6. Now, if you save this Desmos as a new Desmos, it won't alter the original link that you clicked on to get here. So from Blackboard, that's going to default to what it was originally. So you always have that to go back upon or back to. Right? So if you want, you say, okay, well, I'm using this just to roll dice. You could say, all right, well, I don't need this. And then you might look at this and say, well, I don't need these things. Just get it out of the way so you don't confuse yourselves. And there's a benefit to doing that sometimes. If you're working on a nice big screen computer, then maybe you don't have to worry about that because it's easy to keep track of. But I got a limited screen here. I'm doing this on an iPad, so it may not be the easiest thing in the world. I can expand it a little bit, but it's still going to be somewhat restrictive. All right. So now what we want to do here is come up with how many 4s we have here. Now it's not going to be fun to count up all these 4s that exist. All right, so we're going to need another technique to handle that. All right, so you might remember, look at all this is crazy. You might remember some of the graphical techniques from back in Unit 1. That's what we're going to apply here. So I expanded my window a little bit, and so now I'm going to show you how we can count up all the numbers well, we already know the number of numbers, how we can count up the number of 4s in the data set without having to go through the entire data set and say, okay, there's one, there's another, and so on. Right, so we're going to use a technique from the first unit, the histogram approach. So type in histogram. When it goes from italicized print to normal, ordinary, non-italicized font, then you know that you've locked on to a Desmos recognized function. Open paren, and then you'll see it says dataset bin width, so you know you're on the right track. Type in the title of the column containing the data that you want to create a histogram out of. So that's a capital B. You'll see here the default bin width is 1, only because Desmos recognizes that as a reasonable bin width for this data set. You'll see here the bar heights. You have options for count, relative, density. You can align it center, left, and so on. All right. So we'll go count, and what we're going to need is a reasonable window. It looks like this thing maxes out somewhere in the 60 range. We don't need to go any higher than 6, so I'm going to click on this little wrench here, tap on 0, or tap on the lower bound and type in 0. Upper bound for X, I'll make it 7, just go a little north of the highest value. 0, 63 and change is fine, but I'm going to make it 60. All right, gives us a nicer looking view of the graph. All right, so now what we have is a reasonable way of estimating what the value of 4 is going to be, or the number of times 4 occurs. All right, so now it's just a matter of getting that number. So if you keep bringing it in, first thing you'd have to recognize is which one is the 4. All right, so it's increasing order from left to right, 1 to 6, 1, 2, 3, 4. It's the 4th bar. All right, looking at the scale, you can see that we're going by 2s. If you bring it in even closer, it's a little easier to see. Going from 40 to 50, 42, 44, 46, 48, 50, that 4th bar is at the 48 mark. So just by looking at the graph, I'm going to bring this back, we can now say, and we're really just taking the same work from the previous page, except it's going to be, well, I guess I don't need this. It's going to be 300 rolls. We don't need this. Our experimental probability, we can now say is going to be 48 out of 300. Now, just for a quick comparison, we can click on a new field here, type in 2 out of 7. That's the original probability that we got for 7 trials. 48 out of 300 is what we got for 300 trials. Now, 1 out of 6 is about 0.167. So 2 out of 7, we were nowhere near the actual probability. 48 out of 300, we were pretty close, almost spot on to the actual probability of about 0.167. All right, so this is doing a nice job of illustrating the law of large numbers. All right, number 3, 10 marbles are placed in her bag. 9 are white, 1 is red. Using a simulation method, determine the probability of selecting the red marble after 75 trials with replacement. All right, so 10 marbles instead of 6 sides of a die. We can say, out of the 10 marbles, one, two, three, 4, 5, 6, 7, 8, 9, 10. One of them is going to be the red one. So pick one to be the red one. It really doesn't matter. I'll go with lucky number 7. Choose whatever one you want. All right. So our simulation method would have us pretty much doing the same thing, except 75 trials. I'll eventually get there. So the n value is going to be 75. The a value is going to be 1. The b value is going to be 10. We don't need just one single random number. We need 75 of them. All right. So we have our table here, which consists of 75 values. But again, the idea here is that we don't, and you'll see that the table is still 300 units long, but it only contains 75 values. We still want to have a histogram, all right? But you can see and this is the benefit of being able to save your Desmos work, that the histogram has changed to accommodate the new data set. We don't need this stuff here anymore, but this histogram is still referencing the table with column B, and it's still referring to counts. So all I'd have to do is go in and figure out what the height is of the 7th bar. So 1, 2, 3, 4, 5, 6, 7. All right, so that's this one right here. It's right above the 7, so that's a pretty good indicator. All right, now it can be tricky, but if you just kind of line it up with the y-axis, and you can see here the y-axis stays on the graph, or at least the scaling for the y-axis. Even though the y-axis is not visible, the numerical values still stay there. So you can scroll over, you can still scroll over until you get to the 7 bar, and you'll see that that's 5 units high. All right, so we now know that out of 75 trials, 5 were red. So therefore, the probability of getting red would be 5 out of 75. Which is about 0.07. Now, if there are 10 marbles in the bag, 9 are white, 1 is red, the probability of getting a red one is 1 out of 10. There's 10 marbles, 1 of them's red. All right? Experimentally, we just got it to be about 0.07. Not too far away from 0.1, but not close enough. Okay? So what we would do, if we were really experimenting to try to determine this probability, we would try it for more than 75 trials. Maybe we would try it for 75,000 trials, right? But definitely a lot more than 75. All right, or maybe just a little bit more, maybe only 100 trials. But you'd get to a certain point where you level in or level off on the actual probability. Once you get there and you're satisfied that you know what the probability is, then you're done. All right. So that brings us to number 4, 100 random selections. Same question, same general idea anyway, but this time 3 are white, 7 are red. All right. So we have the marbles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So 3 are white and 7 are red. So let's assume that these are the red ones and these are the white ones. All right. Experimental probability of getting a white marble after 100 random selections. All right. So same idea. In fact, we could use the same data set because all we'd have to do is manipulate this so that it would go to 100, but it's still from 1 to 10, and we're still really just kind of looking at the height of the bars. All right, so there's not much adjustment that needs to be made. All right, so if I want white, I'm looking for the sum total of the first 3 bars. All right, so the probability of getting white well, let's see. That first bar, I'm going to bring it in nice and close here. 5 is the halfway point between obviously 0 and 10, 6, 7, 8. So we have an 8. Then the second bar is 9. The third bar, 11, 12, 13. So 8 plus 9 plus 13 out of the 100 outcomes. And again, this is an experimental probability. It's not a true probability because we know that the answer ought to be 3 out of 10. We're going to see how close we can get with this. All right. So as it turns out, 8 plus 9 is 17 plus 13 is 30. out of 100, which simplifies down to 3 out of 10. So we actually locked on to the true probability, but this is an experimental probability. It just so happens that we lucked out by getting the actual probability. All right, the last question is a multi-step process. In the 2015 baseball season, the population mean percentage of instances in which a team scores could depend on whether the leadoff hitter reaches base. Using information below to design a simulation for whether a team scores at least one run in an inning. All right, so you see here we have some decimal values to play with. So we may want to change our whole setup here. All right, go with a random numbers calculator. So you go back to Blackboard and get a fresh new random number calculator. All right. Now, I included a little tree diagram here to give you a sense of what this whole scenario is getting after. But it's basically saying you have a batter, that leadoff hitter, that batter is either going to get on base or not. And then from there, there's going to be a probability of scoring or not. All right. So this actually is the simulation. This tree diagram. So I actually kind of gave the answer, but I wanted to run through a couple of trials of this simulation just to show you how it would work. All right. So the first thing that we would want to do is not get too complicated with this. We don't want to go 100 trials at a time because it's a multi-step process. We have to do a simulation for the leadoff hitter and then a simulation for whether or not the individual scores. All right. So what we would do is just dial this back down to a 1. So n is equal to 1. We would select random number between 0 and 1. So let's get rid of actually everything else. Okay, so when we think about a number between 0 and 1, we can look at it a couple of different ways. We can look at it as just a wide array of decimal values, or we could look at it as any value, since these are 3-digit decimal places, anything between 0.000 and 1.000. All right. So what this is saying is you have a leadoff hitter is going to get on. If you get any of the 0.323, you don't have to actually get the number 0.323. You have to get 32.3% of the values between 0 and 1. So what we would say is anything from 0.000 to 0.323. All right. So that would leave everything else for leadoff hitter not on. All right. So that would be about 0.324 to 1.000. All right. So this is 32.3%. All the numbers between 0 and 0.323 amounts to 32.3% of the available values between 0 and 1. And everything else would be about 67.7%. All right. So we have a random number here. That random number is 0.43, about 0.437. All right. That random number is going to fall in this interval. So the leadoff hitter did not get on. All right. So what happened is we had a batter. The batter did not get on base. All right. So if we had a random number, let me just kind of smidge this around a little bit. All right. So our random number was 0.437. So what this is going to mean is, based off of what we just established, the leadoff hitter is only going to be on if we're living in that 0.000 to 0.323 territory. This is not in there. So what we would say here is the leadoff hitter is not on. I'm going to snag some room here. Now I want to evaluate whether or not there's going to be a run scored, because just because the leadoff hitter didn't make it to base doesn't mean that the team can't score a run. So that's what I'm going to look at now. So focusing on just this piece of it, just this pathway, we would be thinking, all right, what are the possibilities for the scoring of a run? All right, so if leadoff hitter is not on, then we have a 16% chance of scoring at least one run. Score at least one run. That's going to be everything from 0.000 to 0.160. No score would be everything else, so that would be something greater than 0.160 to 1. All right, so we'd be asking ourselves, well, what category does this number fall in? Now we could run the simulation again, or we could just work off of the same value. All right, I'm just going to work off the same value. So the leadoff hitter did not get on. Now this falls in the no score category. So we'll grab another random number. I'll just pull it from the table here. So we have 0.548. All right. So which category? Leadoff hitter on. Well, it's not in between these two numbers, so the leadoff hitter is not on. And then we would want to think about whether there's a score, but we'll get to that in a sec. Let me just copy paste. .548 also falls in the no score category. So we're in good shape there. Now the next value is a little bit of an interesting situation. 0.281. So now the leadoff hitter is on. Oops. All right, the leadoff hitter got on base. So we're not living in this category here anymore. This one, we're now up here. So I'm going to resize. And copy. So if the leadoff hitter gets on, we're in different territory here. We'll just put it that way. I'm going to make it even smaller. Oops. I don't want to copy paste, or I'm sorry, resize all of this other stuff, just this guy. All right, so the leadoff hitter is on. So get rid of this. We're living at, or with 57% chance of scoring a run, so that's 0 to 0.570. Oops. Already had the decimal point there. Make this a little thinner. And then something bigger than 0.570 going up to 1. All right, so that 0.281 has the leadoff hitter getting on, all right, because we're living in this territory here. But then, oops, get out of here. then that .281 is going to fall into this category where we score at least one run. And so that would be an example of carrying out the simulation. You know, it's a little, I want to say short-sighted, but it's not really that. It's just it's not very detailed. It's one particular aspect of the game of baseball, but it's enough to give you a sense, hopefully, of just how this is all supposed to work.